In February of 2019, in the middle of the Greenlandic polar night, a glaciologist named Anders Lund was reviewing thermal imaging data from a routine research flight over the northeastern ice sheet when he noticed something the flight log hadn't flagged: a patch of open water, roughly the size of a football field, sitting in a landscape where every surrounding lake, stream, and meltwater channel had been frozen solid for months. The temperature at ground level that week had dropped to nearly minus 45 degrees Celsius. Lund's first assumption was equipment error, a sensor glitch reading thermal contrast that wasn't really there. He requested a second flight pass 3 days later. The patch of open water was still there, in the same location, the same size, unchanged. It seemed, at first, like a curiosity worth a footnote in a much longer report. A small anomaly in an otherwise unremarkable stretch of ice sheet. But when Lund flagged the coordinates to colleagues at the Greenland Institute of Natural Resources, none of them could offer an explanation that held up. The lake wasn't supposed to exist. Not frozen, not liquid. At that latitude, in that cold, with no visible heat source for hundreds of kilometers, there was no accepted mechanism by which any body of water should remain unfrozen through a Greenlandic winter. The first hypothesis was the obvious one: geothermal activity. A pocket of volcanic or magmatic heat rising from below, keeping the water above freezing the same way hot springs do elsewhere in the world. Lund's team requested a geological survey of the site the following summer. It came back essentially inconclusive in the way negative results often are. No volcanic history documented anywhere in that section of the ice sheet. No elevated subsurface heat flow detected in the underlying bedrock. Nothing in the region's geological record to suggest the area had ever been anything other than ordinary, ancient Greenlandic crust. A follow-up survey the next year, using more sensitive ground-penetrating radar equipment flown in specifically for the purpose, confirmed the same result. Whatever was keeping the lake liquid, it wasn't heat rising from below. Without a heat source, the lake had no business staying liquid. And yet, it did. A visiting researcher named Erik Halvorsen, reviewing Lund's data from Oslo without ever having visited the site himself, argued publicly that the imaging was simply misread, that what Lund's team was calling open water was more likely a thin, highly reflective ice layer, producing a false thermal signature. It was a reasonable objection on paper. Thermal imaging from aircraft altitude has a documented history of exactly this kind of misread. Halvorsen's version of events circulated for nearly 2 years, cited in at least one conference presentation as the likely explanation, before anyone had the ground-level data needed to settle the dispute one way or the other. Settling it meant getting there, and getting there was its own problem entirely. The lake sat roughly 60 kilometers from the nearest permanent research station, across terrain crossed by active crevasse fields that shifted seasonally with the ice sheet's movement. A ground expedition couldn't simply drive out. It required a specialized traverse route, surveyed and resurveyed for crevasse safety, ground-penetrating radar sweeps to confirm the route stayed clear of hidden fractures, and a weather window stable enough to justify days of travel in a region where conditions could deteriorate within hours. Planning alone took the better part of a year, coordinated between the Institute, the Danish Polar Logistics Program, and a small charter aviation service that handled fuel resupply for the Traverse team along the way. The first expedition attempt, in the spring of 2020, was called back after 40 kilometers when a whiteout closed visibility entirely, forcing the team to camp in place for 2 days before conditions allowed a safe return. The second attempt, later that same year, reached the site. What Lund's team found on arrival ruled out Halvorsen's thin ice explanation almost immediately. The water was unmistakably liquid, dark, and, when sampled, startlingly dense. A hydrologist on the team, Ingrid Sorensen, ran a basic salinity test within an hour of setting up equipment on the shore, and got a reading so far outside the expected range that she assumed her instrument had malfunctioned in the cold. A second, calibrated reading confirmed it. The lake's water carried a salinity roughly 8 times that of ordinary seawater, dense enough on its own to depress the water's freezing point by dozens of degrees without requiring any external heat source at all. The lake wasn't warm, it was simply too salty to freeze. Sorensen's working theory, developed over the following field seasons, traced the salinity to an ancient trapped brine pocket, sealed beneath the ice sheet for thousands of years, likely dating back to a period before the modern ice cover fully formed over that section of Greenland, when the area held a shallow, evaporating sea. As the ice advanced over millennia, it had sealed the concentrated brine beneath it, rather than freezing it, preserving a pocket of liquid, hypersaline water, in a landscape that had otherwise been solid ice for longer than human history extended back. Confirming that origin took another 2 field seasons of core sampling around the lake's margins, comparing mineral deposits in the surrounding ice to known evaporite formations elsewhere in the Arctic. The match, when it came, was close enough that Sorensen's team felt confident dating the brine's isolation to somewhere between 8 and 12,000 years, a window that placed its sealing near the end of the last glacial period, long before any written record of the region existed, and long before the ice sheet had taken the shape it holds today. It was, by itself, already the kind of finding that would have justified the years of expedition planning, but the more significant discovery came the following season, once the team began testing not just the water's chemistry, but what, if anything, lived in it. Sorensen hadn't expected to find life. Water at that salinity, in that cold, sat well outside the conditions most known organisms could tolerate. But a sample sent for microbial analysis came back with something none of the team was prepared for: active, reproducing microbial communities, a form of halophilic bacteria adapted specifically to extreme salt concentration and near-freezing temperatures, apparently isolated in that brine pocket for thousands of years, with no genetic exchange with any surface population. A second round of sampling the following year, designed specifically to rule out contamination introduced by the expedition equipment itself, confirmed the organisms were native to the brine pocket and not an artifact of the sampling process. Genetic sequencing placed them as distinct enough from any previously cataloged halophile that the team spent the better part of a year working with microbiologists in Copenhagen before agreeing on a formal classification, a process complicated by just how little comparable genetic material existed anywhere else for reference. The implications reached well beyond Greenland. Researchers studying the search for life on icy moons elsewhere in the solar system, places like Europa and Enceladus, both believed to hold subsurface saltwater oceans beneath kilometers of ice, had spent decades working from models and simulations of what extremophile life in such an environment might look like. Lund's Lake offered something rarer, an actual, accessible, present-day example of a self-contained ecosystem, doing exactly that, on Earth, reachable by expedition rather than by spacecraft. A planetary scientist named Dr. Priya Nair, working on mission planning research tied to a proposed Europa lander concept, reached out to Sorensen's team within months of the microbial findings becoming public. Her interest wasn't in the lake's biology for its own sake, but in what it could teach mission planners about where, specifically, to look once a lander eventually reached an icy moon's surface. Brine pockets like the one in Greenland, she argued, were exactly the kind of localized, chemically distinct environment a spacecraft's instruments would need to be calibrated to detect, rather than searching a subsurface ocean broadly and hoping to get lucky. Over the following field seasons, Nair's team and Sorensen's collaborated directly, testing sampling instruments designed for eventual space deployment against the Greenland brine pocket as a stand-in for conditions no one could yet study anywhere off-planet. It was, by any measure, an unusual partnership, a hydrologist studying ancient Earth brine, and a planetary scientist designing hardware for a moon of Jupiter, both working from the same 600-square-meter patch of unfrozen water in the Arctic. Within 2 years, funding for continued research on the site had drawn interest not just from Danish and Greenlandic scientific institutions, but from international astrobiology programs, and at least one national space agency looking for exactly this kind of terrestrial analog, willing to fund logistics that neither a hydrology department nor a planetary science program could easily justify on its own. None of this, however, was entirely news to everyone in the region. When Lund's team first began organizing logistics for the ground expedition, they worked with local guides from a small settlement, roughly 100 kilometers south of the site, arranging supplies and traverse support through a hunter named Jakob Petersen, whose family had worked that stretch of coast and ice sheet margin for generations. When Lund described the anomaly he was investigating, water that never froze, far out on the ice, with no hot spring anywhere near it, Petersen didn't react with surprise. His grandfather, he said, had mentioned a place like that decades earlier, a dark patch on the ice that hunters traveling that route in winter knew to avoid, not out of any scientific explanation, but because thin, unstable ground near open water in that kind of cold was simply understood to be dangerous. The oral knowledge had never included a why. It had simply persisted, generation to generation, as a location to root around. Petersen's account gave Lund's team something the imaging data alone hadn't: confirmation that the lake wasn't a recent anomaly, but a stable feature of that landscape, for at least as long as local memory extended, likely far longer. It also raised a question the team hadn't fully considered until Petersen asked it directly: if generations of hunters had known to avoid the site without ever needing to explain why, what other unexplained features of that landscape might carry the same kind of quiet, unrecorded knowledge, never flagged to a research institution simply because no one had thought to ask? Today, the site operates under a joint research agreement between the Greenland Institute of Natural Resources and representatives from Petersen's community, with any future expedition or sampling work requiring both scientific and local sign-off before it proceeds, an arrangement Lund's team adopted deliberately after Petersen made clear that the land's significance to his community didn't end where the science began. A small monitoring station, staffed seasonally, now tracks the lake's temperature, salinity, and microbial activity year-round, watching for any change in a system that appears, so far, to have remained essentially stable for thousands of years, through ice ages and ice sheet retreats far more dramatic than anything currently affecting the region. Sorensen, asked recently what she thought the lake still had left to reveal, said simply that a system this old, this isolated, and this stable had likely adapted to changes in ways no one studying it yet fully understood, and that the safest assumption, this far into the research, was that the lake still had more surprises left than the team had answers for. The patch of water Lund first noticed on a routine thermal scan in February of 2019 is still there, unfrozen, in the middle of one of the coldest landscapes on Earth, exactly where it has apparently been for thousands of years before anyone thought to look. If a lake that shouldn't exist has been sitting there the whole time, waiting for someone to notice, it's worth wondering what else is still out there, unflagged, in the data no one's reviewed yet. Subscribe if you want to see the next one we find.